Ladies and gentlemen, welcome back, and we are going to be talking about rule number 3 for delocalization. And rule number 3 says lone pair electrons move toward a pi bond. Alright, so this one is no more difficult than all of the other ones that we've done. It's just a different kind of set of rules that we have to look at. That's it. Alright, so what does this rule actually state? Well, let's say that we have a pretend compound. I'm just going to put an R for random group. And we have a double bond O, and that oxygen, as we know, has 2 sets of electrons. And then over off of this carbon, we have a nitrogen, an NH2, so an amine group. And that also, folks, has a set of electrons. We normally do not draw it, because that nitrogen has 3 bonds, 2 to the hydrogen and 1 to the carbon. And we just know from lecture module 1 that nitrogens are happy with 3 bonds and 1 set of electrons. All right, so rule number 3. A set of electrons can move toward a pi bond. So let's see if this happens in this molecule, and if so, how do we represent it? So does delocalization take place? Well, rule number 1, I see pi bond move toward a positive charge. Well, there's no positive charge here. Nah. Move on. Rule number 2, pi bonds move to other pi bonds. Well, I see a pi bond, but I don't really necessarily see any other pi electrons that are here. So, we move on to rule 3. Rule 3 says a free set of electrons can move toward a pi bond. So here is a free set of electrons. And that free set of electrons is next door, neighbor, to that carbon. And that carbon has a double bond on it. So this does meet the guideline for rule number 3. Delocalization can take place here. What goes on? Well, these electrons can move inward to create a double bond here. This carbon says, no, I can't have 5 bonds. I gotta get rid of one of them. So oxygen, you're electronegative. You want them anyway, so you take it. And we have electron pushing. Delocalization takes place. So I can rewrite this structure. I'll start with the original. Here we go. NH2, and I can erase the dots that were here because those moved inward, and then I can erase one of the double bonds here, and those get pushed up. So that oxygen has an extra set of electrons now that it has to worry with. It's electronegative. It wanted them. It bit off more than what he could chew, but he at least wanted them in the beginning. If this is what goes on, then folks, this nitrogen now has 4 bonds. It becomes positive. And this oxygen, that oxygen now, 1, 2, 3, 4, 5, 6, 1, 7, is a full-blown negative. So out of these two, it will flip-flop. It will go left, and then it will go right, then it goes left, and then it goes right, and then it goes left, and then it goes right, and it will keep flip-flopping over and over and over. However, neither one of these are the true form. It is a mixture. It is a hybrid. So, let's draw the hybrid. We have a carbon, double bond O. We said that this oxygen had 2 sets of electrons. The nitrogen had this NH2 group and a set of electrons here. Now, let's fix our double bonds. We said sometimes that double bond forms right there, but sometimes it gets shifted up, right? So it doesn't stabilize at that location. It's got some movement on it. And we also said a double bond could form between carbon and nitrogen. So I have to show that. And I'll show that with another dashed line. So I'm letting you know these are the possibilities where the double bond could exist. There we go. And sometimes this oxygen, it gets a negative charge. It doesn't stay there, so it's only there part of the time, so it's partially negative. And then sometimes this nitrogen, that gets a positive charge. So yet again, only some of the time, part of the time, part positive. So I can put a squiggly plus and a squiggly minus at those locations to show you where these charges could take place if they're there. Let's look at another one. Let's take something similar. A carbon double bond O, 2 sets of electrons. And then off of this, let's do a CH2 and then an NH2 with a free pair. So the question is, does delocalization take place? Yes or no? And then if so, draw the forms and then draw the hybrid maybe. All right, well, rule number 1, we have pi bond moves toward positive charge. No, there's no positive charge. We move on. Rule number 2, pi bond moves to other pi bond. Nope, there's no pi bond and pi bonds here. There's one pi bond, but not another. So move on. Rule number 3 says, hey, we can get free sets of electrons that move toward a double bond. All right, so we have a free set of electron. It's here. And next door neighbor is a carbon, but that carbon is an sp3 carbon. There's single bonds all the way around it. That means that these electrons cannot move. That neighbor has nothing special to offer or to give. Well, then you're going to look at these electrons and you're going to go, well, what about those? Those are pi electrons too. They are. But folks, these pi sets, these sets of electrons are on an oxygen with a double bond already. I mean, we're not talking about neighbors here. So if you wanted to talk about neighbors, let's talk about neighbors. This particular carbon, if you look next door, there's nothing there. And over on the left-hand side, I just wrote an R group, so you don't even know what's over there. We're just going to assume it's just a carbon chain. And there would be nothing special about that area either. So no delocalization will happen here. Sorry, it's not going to happen, not going to work, and that means all of these electrons are staying put. You are where you need to be, you are where you need to be, you go to your room, you lock the door, you don't come out. They are localized electrons throughout this molecule. All right? Now, let's look at another example. What if we have CH3, and let me erase that mistake. Who knows how that random little wiggly got in there. All right, CH3, and then CH with a free set of electrons. So that means that this carbon's negative. It's a carboanion. All right. Who cares about that stuff? We're just focused on delocalization. Don't let it get confusing. So we want to know, does that molecule show delocalization, yes or no? So rule number 1 says pi electrons move toward positive. Well, there's no positive. Rule number 2 says pi electrons move toward another pi set of electrons. Typically, double bond, triple bond. We have a triple bond, but we don't have more than one of them. We don't have another double bond in there. So rule number 2 really doesn't matter. Rule number 3 says a free set of electrons can move toward a pi set. And a pi set is normally double bond, but folks, it can be triple bond as well if we see those, because those are pi electrons. So I do see a free set of electrons. The free set of electrons, they're right there. So I need a question next door. Well, if I go left, there's nothing over there going for it. If I go right-hand side, folks, that is a sp2 carbon, and this is really an sp carbon because it does have another set of p overlap. So I do see electron movement. All right, so if I redraw the original, CH3, CH, C, triple bond, CH. Let me write that a little bit better. And then here I have a free set and a negative charge on that carbon. And I wanted to show you another resonance form that this could take place with. Well, what we could do, this free set of electrons right there can move inward. because next door there are pi electrons. So we could see a movement of those pi sets here to form a double bond. If that goes on, folks, that carbon now has 4 bonds. 1 to the hydrogen, 1 to the methyl group, and 2 to the carbon next door. But this carbon says, I've got 5. I need to do something with them. So I'm going to take one of these bonds, I'm going to shift it next door, and put it here. And I'm going to force that carbon to take 2 extra electrons than what it originally had. And because it took extra electrons, which is extra negatives, it's now a negative charge. Look at there. There's a resonance form. All right, well, what about a resonance hybrid? Okay, we can show those. Not a problem. No big deal. I'll start with my original, and this is how I'll do it. There we go. And what I need to show is that sometimes a double bond could happen here. We showed that in our form that we drew up above. And then sometimes that triple bond is not really a triple. Sometimes it's just a double. So I need to change that one to a dotted line. Then that also means that sometimes this carbon is not fully negative. This is a squiggle minus. Sometimes it's negative, sometimes it's not. It's neutral. And then this N carbon, look, we drew a negative charge there, didn't we? So sometimes that carbon is also negative. And we can do squiggle minus there as well. Well, there's a resonance hybrid. Are those getting easier? I hope. I hope. If not, we'll keep doing examples. I mean, that's what this lecture is all about, right? So let's look at another. CH3, and then we do CH, double bond, CH, and then we do O and CH3. So the question, does delocalization happen? If so, write the resonance forms and then end up with a resonance hybrid. All right, so let's see what this structure is going to give me. Rule number 1, delocalization. Double bond moves toward positive. No positives. Number 2, delocalization. Double bond moves toward another double or triple. Sorry, I only have 1 double bond here to worry with. Rule number 2 doesn't apply. Rule number 3, a free set of electrons moves toward a double bond. And I look at this molecule and I go, there's no free electrons here. So rule number 3 doesn't exist. That's the only rules that I know at this point. I told you there were 4. What's rule number 4? Well, I'm going to stop you there. Because they did a trick. They drew the structure this way. They did not draw the full structure because if they did, this oxygen has 2 bonds, and folks, it also has 2 sets of electrons. That's the way it always has been. Oxygens are 2 bonds in 2 sets. Nitrogens are 3 bonds in 1 set. Halogens are 3 sets. This is something that's never went away. It's something that we've talked about. It's just kind of coming back to haunt us a little bit now. So if I look at this molecule, now rule 3 does apply. I have a free set of electrons, 2 of them actually, and I look next door. So I look to the right, there's nothing going for it. I look to the left, and lo and behold, look, it is an sp2 carbon. There is a double bond that's there, folks, so a free set of electrons will move toward a double bond. So I'm going to redraw the structure. CH3, CH, double bond, CH, oxygen, CH3. Here's a free set of electrons, and this is how we do it. 1 set of electrons will be pushed, and it will go here next door. When that happens, folks, this carbon now has 5 bonds. 2 to the O, 2 to the carbon to the left, and 1 to the hydrogen. Can't have 5. So it's going to say, all right, I'm going to have to get rid of one of these, And I'm going to have to push those electrons over on that carbon next door because he's willing to take them. So I'm going to push them over. So when this happens, let's take a look at here. This oxygen formal charge, well, it's normally a 6 valence. Right now it has 1 from the bond, 2 from the bond, 3 from the bond, 4 from the dot, 5 from the dot. Well, this is now a partial positive, or a full-blown positive really here at this point. The carbon over here, well, normally that's 4 valence. 1 from the bond, 1 from the bond, that's 2. 1 from the hydrogen bond, that's 3. 1 from the dot, that's 4. 1 from the dot, that's 5. 4 minus 5, -1. So this is a negative charge. Look, I did it again. I'm getting ahead of myself. All right. So this is a negative, and this will be a positive. Well, there's one form. There's no really other forms that could exist. The molecule is going to flip back and forth between these two variants of the molecule. I think that out of both of these sets, we look at which one would be more stable. The more stable ones are always the one without the charges that are formally assigned. So out of these two, this one is going to be a more stable form than the other one because this one has a full positive and a full negative on it. Anytime those happen, they're not going to stay around very long. So now I need to do a resonance form. I'll start with my original. I'll just rewrite it. And if I look at this particular type of molecule, this double bond, in that form, it's not really there. So it's only there part of the time, right? So I'm going to do a dotted line that represents that double bond that's only there part of the time. I'm also going to look at the carbon on the right-hand side. There's a double bond that did form. So that means I need to do a dashed line there as well. So there's 2 dashed lines. The free set of electrons aren't there all the time. That positive isn't there all the time. So that's a partial positive. And this free set of electrons, they're not there all the time. So therefore, that is going to be a partial negative. And there you go, folks. There's the representation of the hybrid molecule. Here's another example. Does it show resonance? Here, the answer is just a simple yes or no. That's all that we're after. Does it show resonance? Well, this nitrogen, keep in mind, they're not showing you the whole thing, has 2 sets, or 1 set of electron, 2 dots. Well, here's a free set. Next door is a carbon. That carbon has a double bond on it, so ding ding, yes it does. Those electrons will move, delocalization will happen, and it changes the molecule for that reason. That's all that this question wants, nothing more than that. Here's another one. Does this molecule show resonance? Yes or no? All right, so here's a carbon, there's a carbon. This carbon, look, has an oxygen. This carbon has a double bond. This carbon not only has the oxygen with the pairs, but also a double bond as well. So this carbon has a double bond, which is a pi set, and next door is a carbon with a pi set. So pi can move toward pi. This is rule number 2. Ding, ding. Yes, it does. This does show resonance. These electrons can move here, and that forces these electrons to move up here. I can get movement through that area of the molecule. Here's another type of question. Which of these, if any, show resonance? All right. So let's take number 1. Let's use the rules that we have talked about so far. The fourth rule I've not really mentioned because that's a single electron, and single electrons behave just like a pair of electrons would. So think of rule 3 and rule 4 the same. One just represents a pair, and one represents a single. All right? So let's take a look at example 1. Is delocalization here? Well, look, here's a double bond, and it's right next door to another carbon with another double bond. That in itself, ding ding, yes it does. So how would this move? These double bonds, or the free set, can go here, this free set can go there, this free set can go there, and we can get movement all the way around in that case. So delocalization can take place. Number 2, here we have a double bond, there we have a double bond. So rule number 2 is in question. Can a pi bond move toward another pi bond? Well, here's a carbon that has the double bond. Next door to it is a carbon that doesn't have squat. Just single bonds. That other double bond out there, it's too far away. This is not going to show delocalization. Sorry. It needs to be closer if that's what's going to happen. Molecule number 3. If I look at the nitrogen, I need to clean this up a little bit first, right? I'll look at the nitrogen. It has 1, 2, and third bond to the hydrogen. So 3 bonds, and there is a set of electrons that will be there in the nitrogen. They're not drawn, but they're understood to be there. So even if you didn't know that, you would still get the correct answer. Because look, we have a double bond. That carbon is involved in the double bond, and next door to it is a carbon that's also involved in another double bond. So a double bond is near a double bond. Pi moves to pi, so rule number 2 is satisfied. So ding ding, yes, number 3 shows delocalization. But more so than that, folks, it also goes up into the nitrogen as well. These pi electrons can move here, and that will force those pi electrons to move to the nitrogen, and then these can also move in to the ring. So we get movement through the entire thing here because this is pi moving to pi, and these can be free electrons moving to pi as well. So rule number 2 and rule number 3 are in play here. All right, let's take a look at group number 4. Structure number 4 down here, I look at this molecule, I see the oxygen. Folks are doing the same trick. They understand, or they think that I understand, that 2 sets of electrons are there. So I need a question. Rule number 1, does the pi electron move to positive? No, there's no positive. Rule number 2, does pi move to pi? Well, there's only one double bond really, so rule number 2 we can kind of leave out. Rule number 3, free sets move to pi bond. All right, well, I have a free set and I have a pi bond. Are they close enough? Well, if I look, the free sets are here. On the neighbor, it's all sp3s, all single bond. On this neighbor, same thing, all sp3s, all single bonds. This is not going to show delocalization there. It's too far away. Next one, number 5. Number 5, I scan through the molecule. Again, I see the nitrogens. I know that those are going to be areas that they're going to try to trick me with. The nitrogen has 1 bond pointed up, 1 bond to the hydrogen, 1 bond kind of pointed down and off to the side a little bit. So this does have a free set of electrons that's not drawn, but they are understood to be there. So rule number 1, I don't really see a positive charge. So pi moves to carbocation. It doesn't apply. Rule number 2, alkenes and alkenes, double bond, double bond, double bond, triple bond. I see only 1 double bond here. That's it. So rule number 2 is not going to apply either. And then rule number 3. All right, so rule number 3 is going to involve free pairs and double bonds. And I have both of those in this group. So there's a possibility delocalization could happen. Let's go up first to this neighbor. That neighbor has nothing but single bonds on it. It's a carbon with 2 bonds and 2 hydrogens. So nothing special there. Delocalization's not going to happen. That is not a better place for those poor little electrons. And then I go to the bottom right. Notice how this kinks down. That means there's a carbon right there, folks. That's what that means. So that different direction is a sign that a carbon is present, just like it was up here. So that carbon, nothing special. It's sp2. It has all single bonds all the way through. So these electrons have no reason to move. So this does not show delocalization for that reason. Hopefully those examples are getting easier. If they are, then that means you're learning delocalization. It just really requires example problems and working with them over and over and over in order for you to feel comfortable with them. But folks, that's the story of organic anyway. It doesn't really matter what we're talking about. We need examples so that way we can kind of explain these types of situations again and again and again in order for them to make sense. Something else I want to leave you with before I stop this video is an idea that we threw out kind of in the last video, and this was about stability. So here is an example of 2 different resonance forms due to delocalization. What you see here is a free set of electrons that move in, and then it's moving in because that carbon is sp2. It has a double bond on it. So those sp2 or a set of those electrons are going to be pushed up to the oxygen up above. When this happens, we end up with this form that you see over on the right-hand side. The double bond has now formed here. The oxygen saturated, it's a positive charge, and then this oxygen saturated with negative, so it's a negative charge. Notice that these separated charges are on the molecule. So the question is always, which one of these resonance forms would be more stable than the other? If you see these positives and these negatives, folks, no. Those are not stable. Those full-blown positives and full-blown negatives do crazy things when it concerns the chemical structure of these compounds. So if I had to choose between 2 different versions, and one of them I see full-blown positives and negatives, and the other one I don't really see full-blown positives and negatives, do I? It looked like a normal structure to me. That is a very good sign that the one over on the right-hand side does form. It forms temporarily, but then the molecule will rearrange itself back to give me what I started with. All right, so this will continue. It will flip-flop back and forth. It will always flip-flop back and forth, but out of the 2 versions, it does have a preferred one that it does like. If you look at these 2, folks, here we have on the left, I see a carbon double bond O, and then an oxygen that slants off to the right-hand side with a full-blown negative. And then on number D, I see a carbon double bond O that points down below, and then an oxygen with a full-blown negative. And it says, which one of these is more stable? Well, I'll look at this, and there's not really a difference, is there? Between C and between D, there's not really a difference. So here I see the negative on that side, but so what? I see the negative, and the only thing that it's happened, it's moved up. So it's still there. There's no difference in it. The double bond O, well, that double bond O is still there. It just switched sides. So these things are kind of equal, and that's okay sometimes with resonance forms. They can be equal. I mean, that's not a big deal. So when this molecule flips back and forth, there's not a preferred way that it wants to be in. So sometimes it will kind of fully go to molecule C, and sometimes it will fully flip to molecule D. And then it will flip back to C, and then it will flip back to D. And there's not a preferred side that they would prefer to be on. And that's okay, especially in the world of delocalization. All right, so that's it for this video. And we'll keep doing example problems, and we'll keep talking about delocalization in the upcoming slides.